Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host as usual is Tobias Macey, and today I'm interviewing Rolando Garcia about FLOR, a suite of machine learning tools for hindsight logging that lets you speed up model experimentation by checkpointing training data. So Rolando, can you start by introducing yourself?
Of course. Thank you so much, Tobias. So I'm a PhD candidate at UC Berkeley, which means that I'm very close to graduating and getting my PhD. I came here, I'm advised by Joe Hellerstein. He's an expert in databases. So this will be my fifth year. I started at Berkeley from Arizona State, and I have had the opportunity to collaborate with companies like Amazon, as well as recently work with a startup in a similar space. I think throughout my studies here at the PhD level in Berkeley, I have focused on the model management lifecycle, which now recently has a more convenient acronym of MLOps.
Yeah, MLOps is definitely a term that's been gaining a lot of ground recently. Do you remember how you first got introduced to Python?
When I was learning Python, the other languages that I knew was Java and C#. I came across Python as a consequence of wanting to learn AI. I was trying to teach it to myself. I was a student at Arizona State, and I wanted to learn the greatest and latest AI tools and techniques at the time. So what I had access to were online courses, so MOOCs from Stanford and Berkeley. So I don't know if your audience will be familiar with the Pac-Man project that Berkeley hosts on edX or Coursera. So I started participating in that. I started doing the Pac-Man project activities, and that's how I started to learn Python. This was around 2015.
That brings us now to the project that you've been working on recently called FLOR, or FLOR, for Fast Low Overhead Recovery. I'm wondering if you could just describe a bit about what it is and some of the story behind how it came to be and why that was a problem that was worthy of your attention.
So FLOR, the project here, when I entered in my graduate studies in 2017, I joined the RISE lab, which was a successor to the AMP lab at UC Berkeley. It was being headed or directed by Jan Stojka, Raluca Popa, Joe Hellerstein, and Joey Gonzalez. So jointly, they were experts in systems, security, databases, and ML or ML systems. So it was a really fortunate combination of experts at Berkeley. I came in and I was advised by Joe Hellerstein, and I was working very closely with Joey Gonzalez, an ML person. When I came into the lab, there was a project called Clipper, headed by Joey Gonzalez, that was meant for low latency prediction serving. So the question that Joey had said to me during the interview was, assume that ML works and AI is working as it is, so we've made enough progress. How do we get it out there? How do we deploy it and maintain it? Kind of moving beyond the basic questions of model training. So Clipper allowed model developers to deploy their models and serve predictions, kind of like the ML as a service mentality or spirit. And the next step then was the pipeline automation. So building pipelines that trained models and then were able to automatically deploy and maintain those models. So machine learning models have degrading performance over time, or their quality can degrade. So they were working on a system called Jarvis that would help model developers train models and then upload them or update them as necessary to maintain service level objectives. So that was a system that was being headed at the time that I joined. Another project that was being developed was called Ground, which was a data context service. And the aim of Ground was to manage the lineage, provenance, usage, history, and logs of data. I think we've known several headline stories about 538 misreporting some incident as a consequence of a lab accidentally clobbering a data set that they didn't really understand where it came from. So when Joe and Joey discussed together kind of like what the problems were around model management and also this context management, we found that the problems that we saw with data management were exacerbated with model development and model management. And so not long after that, we published a paper on context, the missing piece of the machine learning lifecycle. And so the idea was, can we build a system that allows model developers to train a model that allows them to flow easily between the development and production environments, and long after production allows developers to answer questions about failures, for example, that happened months ago, because we know that machine learning has these long failure horizons. So FLOR is flower in Spanish. It came about as like sprouting from ground. And so data context service was such that the model developers at first had to write a DAG or workflow, kind of like you would in Airflow, for what the execution was. So you had a data preprocessing step, and you had a model training step, and then you had a validation step, and so on. And when we met with sponsors at like poster sessions, one of the comments that I repeatedly heard was that people were not interested in rewriting existing pipelines, mostly because of trust and reliability. Something that a person said that really stood out to me was that they had a model training pipeline written in Perl 7 years ago, and the engineer who had written that pipeline was no longer at the company. And so they said, this is something that runs routinely. We're not interested in rewriting it for FLOR. How can you help us? So that's kind of where we started. And then the journey changed pretty drastically from there to answer the question, what's the most tooling or what's the most support we can provide to a model developer without asking or relying on any kind of cooperation from them? So this could be because we have a data scientist who's a domain expert and a non-technical user, or it could be someone who's working at a company and they're just working against a deadline, and so they don't have time for these like best practices. So what does the tooling look like? And one of the first lines of research of FLOR involved program instrumentation, to be able to provide this kind of tooling without the user having to have that direct manual control.
You mentioned that FLOR came out of the ground project in order to be able to help with this question of context, and particularly when building and training machine learning models. And I'm wondering if you can just talk to some of the fundamental challenges that people experience when they're going through that model training and experimentation process, and some of the utilities that FLOR provides to help remediate those issues.
Yeah, so there are two problems that we focus on with FLOR with model training. I guess the more fundamental problem is that engineering best practices are at odds with the exploration flexibility and agility. When people are exploring properly, it's almost like playing in a sandbox. And the last thing they want to do is be very methodical and meticulous about record-keeping practices. And so I guess the challenge is one of human behavior. It's how do you ask people to record, keep track of everything that they're trying so that they can learn from previous mistakes, build a coherent theory about how machine learning is working without having this burden then slow down their speed of iteration. Because we know that for machine learning, the number of alternatives that you can try in some allotted block of time, the more you can try, the better your performance is going to get. It's a very empirical science. So that was the first kind of like the fundamental problem. And the more immediate one that was kind of irritating for us in the lab was that there were some folks that were rerunning model training jobs. And in a lab at Berkeley, that could be something that runs overnight or can take as long as a week to train. And they would see that the model wasn't learning anything, it was flatlining, and they wouldn't understand why. And then when they would return and look at their code, they would realize that they were missing a logging statement. So that kind of missing a logging statement in training, it's not like in systems where you can just sometimes do that cyclic debugging pattern. It takes very long. So it was one of those things where the execution is long running enough and the data is valuable enough that we need to have some tooling to recover it.
In the absence of something like FLOR, what are some of the ways that machine learning researchers and engineers might address that problem, and some of the strategies that are, maybe band-aids on the solution, but are ultimately too cumbersome to be a standard practice?
The work that we've done in FLOR evaluated, and we have an accompanying publication on VLDB at a conference. Your question reminds me of something the reviewer asked. And what we ended up doing in the paper, one of the baselines that we compared against for FLOR was a hand-tuned or expert approach. So everything that FLOR does can be done by hand with proper methodology. If you take periodic checkpoints and you are serializing the model parameters and the optimizer parameters, you're probably going to be fine. The way that you use those to answer questions, I feel like once you understand kind of the post hoc analysis or the hindsight logging way of doing things, you can do yourself. I actually think that's infinitely more valuable than having a tool. If we're able to distill what these minimal best practices are that someone can reproduce even without adopting any tool. So people already follow checkpointing practices. What they do with those checkpoints, I think they can be more creative about it. So usually the regular checkpointing that people do, they might use it for warm starting model training, or they might use it for fault tolerance. Like if a model training run dies after 178 epochs of training, they might want to pick it up from 179 and continue. But with hindsight logging, if you missed a logging statement and you want to reproduce the entire execution, this is a great opportunity for parallelism. You could have one worker do the job from 0 to 178 and the other worker pick it up from 179 and continue. So you know that you can use this for data recovery, these kinds of like checkpoint resume by dispatching parallel workers simultaneously. So that would be one example.
In terms of the FLOR project itself, can you talk through some of the ways that it's implemented and some of the design considerations that you built in to make it sort of a low overhead in terms of implementation, but also low overhead in terms of actual execution?
FLOR is entirely in Python. I've had actually the fortune of working with many undergraduate students at Berkeley, some of whom went on to receive their master's degrees working on the system. The first student, Eric Liu, worked on background materialization. And the idea was, how can we have the main thread or the main process focus on model training and have the other cores, of which there are many in these clusters, help with serializing the data and then writing it to disk, just to further reduce logging overhead. And this actually turned out to be a very Python specific problem, because anywhere else you would just solve this with multi-threading. You would solve this problem with multi-threading and do that kind of concurrency control. Python has a global interpreter lock, and so that was a real option for us. We then started thinking about, well, do we have multiple processes and they communicate with each other? They pass the tensors around. Eric evaluated multiple different alternatives, and the reason why they were eliminated was because serialization was very costly in our setting. So serialization ended up being 4 times more expensive than writing to a file. And so if we have to serialize something to put it into PyArrow, or if we have to serialize data to put it into a queue that gets message passed, that's going to lead to too much overhead. It's almost not worth it. So the way that we ended up solving that was with fork and copy on write semantics. So this is data that is going to get written once. So fork serves as a kind of one-shot, one-way IPC. And we copy the data and the child process does the serialization. So we're able to get some savings on overhead there. One of the ideas that was explored was writing low-level code in something like C or C++ for this kind of multi-threading background logging. But again, we saw that it wasn't really necessary with fork. So we were able to just stick with vanilla Python. And then for the other pieces, there's adaptive checkpointing, and there's also the instrumentation piece, which rewrites user code to do this automatic checkpointing and this automatic resume. That we use the standard AST library as well as Astor. And I also want to give a shout out to Green Tree Snakes, which is documentation for AST parsing and transformation in Python that I think is very valuable. I heard about that library from Jonathan Riggett and Kelly. I think he's now a professor at MIT. Very early in my graduate career, but it's been one of the more useful documentation sites that I've used.
In terms of the evolution of the project, you mentioned that early on you had one particular direction and then ended up sort of shifting focus. I'm wondering if you could just talk to some of the initial ideas that you had about the problem space and some of the ways that your thinking on the potential solutions has changed and how that has been reflected in terms of the evolution of the implementation of FLOR.
I think on the very early days, we ended up looking a lot like something like Amazon SageMaker or MLflow, for example, where you can specify pipelines that later execute. So the goal here was to reduce some of the friction between development and training. So we kind of were aware that data scientists, who may be economists or physicists, might write some of these models, but then they need to train at scale. Someone has to take them from Python and rewrite them in C++, and then they make them capable of distributed training. And then there were other issues like that. And so we thought that by making the language match something that was more production oriented from the beginning, that we could avoid some of those problems. But they just ended up becoming barriers to adoption. So we started to move away from that. Instead of asking people like, well, tell me what the inputs are, what the computation is, what the computation produces, and then where it writes it to. You can see that a lot of that information is already encoded in the program, just the way that programming languages work. A lot of that structure is already there. So a function name can tell you, roughly what the function is trying to do. You know how many inputs it has. You can do some kind of duck typing, like runtime checks, to see what data is coming in, do some hash checksums to see how it's being transferred and connected. And so we started kind of moving towards a direction of what's the most we can infer ourselves without involving that direct intervention from the user.
As far as the core engineering problems that you had to build into FLOR and maybe some of the sort of API design to make it approachable for people who didn't want to dig into the specifics of what this is actually doing under the hood, wondering if you can just talk through some of those considerations and some of the challenging elements of actually building this library and making it accessible for people who just want to get their job done.
I think the core engineering contributions would be the background materialization, adaptive checkpointing. So the model developer can choose the kind of logging overhead that they're willing to tolerate. The default is at 6%. And then the system automatically throttles the period with which the model is checkpointed to make sure that that target is met. We do that through runtime checks, runtime analysis. And then in addition to that, I think the core of the implementation of the engineering challenge was instrumenting Python code. People who work with Python, people who work with program analysis know that the same reason that makes Python so easy to start using off the bat makes it very difficult for a static analysis engine, so you have to make some kinds of assumptions. For FLOR, one of the things we want to do is with memoization, if we're skipping a block of Python code during replay for speedups, we want to make sure that we capture all of the relevant side effects. And when you have Python calling functions, and then later they go out into C or something else, that side effect estimation is non-negligible. So we do a side effect estimation. It's an over approximation of the side effects of a block of code. And so that gets selected for checkpointing. Getting that right was a technical challenge. Determining what the side effects are, it's not possible to do a confirmation or a verification that you were able to checkpoint the state correctly without incurring large overhead. And so one of the ways that we got around that was because of our specific logging scenario. So in the first execution during model training, we assumed that the model developers log some data, such as the training loss. And we assume that on replay, they log that same information. So that serves almost as a fingerprint to compare the replay fidelity to the record case. I know another challenge, for example, was that just kind of the expectations, record replay in other communities, you can brag about like a 24x overhead, like if it's JavaScript that you're trying to run on a computer instead of on a mobile device, such cases. But in our case with model training, you can always just rerun training. So we have this strict less than 2x ceiling on overhead. So kind of like being very aggressive about favoring a system that doesn't lead to these burdens, but still is able to provide significant speedups at replay time.
And so for somebody who is building their model training, they want to be able to take advantage of the utilities that FLOR offers. What's the process for actually integrating it into that model development process and then being able to speed up the iteration cycles for successive experimentation runs and changes in model behavior?
We have two modes. We kind of have like a hands-free mode where from the command line you call FLOR and it instruments your training script for logging. We also have kind of like an expert mode or an expert API, which is the one that I prefer to use right now. It makes debugging easier. I guess I can return to that point later, but debugging instrumented code is kind of its own hassle. With using the manual API, you import FLOR, you tell us what the main loop is. So there's an iterator, kind of like for epoch. The main loop is the one that iterates over model training epoch by epoch. And then you memoize the nested training loop to checkpoint the model and the optimizer periodically. And so that gets you the background logging, the adaptive checkpointing, and the fast replay.
And as far as the checkpointing and log structures that you implement for being able to, jump to a particular point in the training cycle, what's the actual information that you are storing there to be able to rehydrate the model at a particular point in the training cycle?
We store some metadata like the static identifier, the runtime identifier, so something can get called multiple times in the same execution. The name that is given at the program level, which is usually pretty descriptive. It's something like loss model. And then we serialize the data. And again, serialization in Python is not something so simple. For developers who are listening, we use Cloud Pickle. Of all the alternatives that we've tried, it's been the one that is the most robust. I think the only thing that it can't handle is serializing generators. But other than that, it does a fairly good job. And fortunately for us, again, we're kind of building on existing practices. So TensorFlow, PyTorch, they already provide their own serialization primitives. So FLOR is just able to detect that it's dealing with an object, a Torch object or a TensorFlow object, and it's able to call its appropriate dictionary, elicitation routines, and then serialize those. So what ends up being written is on one checkpoint, there's a collection of log records that are written. And each log record will have the metadata, the name, and then the serialized value. And at replay time, it's able to accommodate those values the same way.
And as far as the integration aspect, sort of machine learning ecosystem for Python has been growing and exploding over recent years, particularly in the deep learning space, with PyTorch and TensorFlow being the dominant players, but there have been a lot of other entrants into the ecosystem. I think JAX is maybe one of the more recent ones. And I'm wondering if you can talk to what the level of support is for FLOR for each of these different libraries, or maybe some of the ways that you have engineered it in order to remain agnostic to the specific machine learning framework that you're operating on.
We definitely want to be agnostic and supplementary to these systems. We want to be able to work with logging libraries like TensorBoard or weights and biases. So that's kind of the natural ecosystem. If people are using the manual version of FLOR that doesn't do instrumentation, then they'll be able to integrate it into their Python workflows the way that they would any Python library like NumPy or Pandas. If using the more advanced instrumentation library, like that might have some side effects that we need to think about more carefully. So FLOR, the manual mode of FLOR is going to be, if you know how to use TensorFlow and you know how to use PyTorch, you're going to use FLOR in a way that integrates those properly. For the automated hands-free mode, for side effect estimation, I think that's where we do rely on PyTorch or PyTorch semantics, just because we're able to specialize. And we haven't tried it with TensorFlow. I know that the TensorFlow lazy syntax it's different, so I don't think we would be compatible with that. But the more eager syntax of TensorFlow is definitely something that just, even for the instrumentation library, that should be simple patch. It's just something that was out of scope at the time of publication.
And so for people who start to adopt FLOR as a component of their machine learning experimentation process, what do you see as some of the long-range impact in terms of their productivity or the quality of the models or the types of experimentation, or maybe just sort of shifts in terms of how they think about building and experimenting on models?
I think the first consequence is just more data or more of a record available for analysis after the fact. I'm not sure what all of the different instantiations of that might be. I have some examples from students that I think are quite creative. I mentioned earlier that one of the horror stories in the lab was that people were training models, finding a missing logging statement, and then rerunning that whole execution. But I think the truth, or the more common case, was even scarier than that, which is you forgot the logging statement. It's going to be too expensive to rerun, so you just kind of make a guess and move on. And I think that attitude is around. Again, I haven't quantified it, but that's my impression. And I would like to know, how much that contributes to our current conception of ML and AI as this very foggy, obscure thing. And I think part of it is because we're not really having this record that we build off from, that we can improve and iterate and form this theory about why things are going wrong, or kind of confirm our hypotheses. We might say, well, the reason why the model training failed was because there was a dead ReLU, or maybe it failed because of exploding or vanishing gradients, or it might have been reward hacking, like one of these particular problems. But if you're not able to get to the specific cause of that problem because it's too expensive to collect that data, you're not really learning from your mistakes. So I think kind of creating a culture where long after a model has been deployed, people can revisit training and ask these in-depth questions, or people can, after something goes wrong, are able to recover the data and do this analysis instead of just skipping it, can help with our theorizing and hypothesizing about how machine learning works and how we get better at it.
Beyond the point that the model has been trained and you've settled on the specific architecture or the specific solution to the problem that you're trying to solve for, what is the long-term utility of FLOR? Is it that it's only useful in the context of doing the initial training and experimentation, or is it something where you would keep FLOR as a component of your model training as you go through successive iterations of accounting for model drift in production and dealing with some of the long-term maintenance of models to ensure that it is operating efficiently and that you don't have to worry about shifts in concept and the various kind of productionization concerns that go along with it?
So FLOR is going to be the lab that I'm a part of. The RISE lab is named that way for real-time, intelligent, secure, and explainable. FLOR is definitely a project in the explainability realm of the lab. So as far as development, training, and deployment goes, the long-term vision of FLOR is to aid with that explainability, to aid with the analysis. And you're right to point out that training is only part of the story. Especially in machine learning, and more so than in other areas, failures are non-localized. You can have a model that trains and it fails because it didn't reach an accuracy higher than 75%. Or it might actually not fail on your data and only fail on data that it sees post-deployment, just like you said, because of distribution drifts or other reasons. And so it's possible that even though you had no reason to look into the training at depth at the time, you might need to return to this data, not a day, but maybe a week or a month after the fact. And so it's very important that all of the context that was there at the time of training is still available post hoc so that the model developers can answer their questions and get to the root of the problem.
And so in terms of actually maintaining that contextual information that is generated during those training cycles, what are some of the useful strategies as far as being able to store that over the long run and being able to categorize that so that you can retrieve it and reanalyze it when you hit the point where you say, okay, this model trained and it hit 90% accuracy on this data set. Now I'm going to put it into production and, oh shoot, now it's only operating at 60% because my training data wasn't representative of the real world, and sort of managing that more sort of long-term, long horizon workflows to be able to reanalyze that context and just some of the cataloging aspect that goes along with it.
Yeah, hearing you now reminds me of kind of this ideal that has been going on around, which is to make work self-documenting so that, ideally you kind of just do your own work and the relevant records are entered automatically. And then you can just ask questions from this oracle about what happened in the past. There's an answer. Maybe I'm a pessimist. I think that might be too hard for us to achieve. At least I've wrestled too much with managing context. And so I tend to believe in something a little weaker, but I think it's almost just as good, which is you should have the freedom to put in the work to annotate things at any time. And that context shouldn't degrade. So it's one of those things where, like you say, how do you capture stuff almost in the raw, but enough of it so that someone can come in with a highlighter later and tag it and give it the appropriate meaning? That's actually leading into the work that's ongoing in the FLOR, some of the next steps, where it starts to look a little bit more of like a database where we interact with it, by inserting logging statements or posing queries. And then the record replay serves almost like as a query execution engine underneath. So some of the things that we're exploring, what are the things that you need? The code, the source code, you need to version automatically. So that's currently a challenge. Auto versioning is something that we tried very early on in the project 5 years ago. And we kind of kept taking it out of, putting it in the back burner and then returning to it. And the reason is that it's easy to do poorly. There's a lot that model developers work with as far as data. It can be spec files. It can be the different Python environment, the virtual environment that they're using. And different users have different preferences. So right now we're focusing on versioning the code on execution and focusing just on that code. And the checkpoints enable us to replay that execution efficiently after the fact. So I think what other context we need in order to be able to answer those questions, in deployment time, we're going to need records of the inference that the model made. I guess I can speak in general terms about what the information is that would be necessary, as well as the information that FLOR collects. FLOR is definitely right now focused on a narrower piece of context, which is one that revolves around training.
The other interesting aspect is that for most people, as they're going through the initial experimentation process, they might just be running on their laptop, but depending on the quantity and scale of the data that you're working with or the overall size of the model, you might hit a tipping point where you actually need to start thinking about distributed training using something like Horovod or some of the other projects that are out there. And I'm curious what level of support exists in FLOR for being able to support those distributed training use cases. And if it doesn't have anything now, what you see as some of the necessary work to be able to grow to support that, or if that is just completely out of scope for the problem that you're trying to solve for.
It's not out of scope, but it is a difficult question. I think on replay, we auto-parallelize an execution. And part of the reason why that's so simple for us is because it's a single chain of instructions that we're parallelizing. So for people familiar with the record replay problem in systems and software engineering, they know that if you're trying to find the root cause to some failure in an Oracle database, you're going to have to trace logs or dumps of a service that was running, continuously for many months. Kind of replaying the conditions that led to that bug is arduous, and you need a very high fidelity. And what that problem ends up looking like is like turning a multi-processed distributed execution into a single thread so that facilitates reasoning. It could be like a topological sort of a distributed execution. In our case, it was almost the inverse of that. We took this thread or this chain of instructions and then we parallelize it, which is more in line with the tradition of transaction recovery, like the work in Aries for transaction logging. So when we consider distributed training cases and we consider finding a temporal ordering of the logs, in this case, it's non-trivial. So it's not something that we support yet. We have some partners who work in companies like Meta and Google. We maintain open lines of communication there. It is definitely an extension for distributed training. Logging and distributed training is in scope, but it's just not something that we've been able to complete to this point.
Another aspect of the work that you're doing is that you are a researcher, you're doing your graduate studies. FLOR is an open source project that you're maintaining as part of that work. And I'm wondering if you could just talk to some of the aspects of maintenance of open source projects when the core purpose of it is for research oriented goals, and just some of the ways that that might contrast with other types of open source that people might be used to, where maybe it's a hobby project from somebody who's doing it in their free time, or it's a project that is open sourced as part of somebody's day-to-day work at a corporation.
So I'm fortunate to be a member of the RISE Lab, and we have a pretty good track record as far as commercializing projects goes. Our predecessor lab, the AMP Lab, led to the launching of Spark and Databricks, now the company that maintains it. And the RISE Lab, Ray, and Anyscale, I know you mentioned Horvat, might be other systems in that space. I think we definitely have the support for, rigorous software engineering and development. A lot of the times, though, it's a matter of team size. And so in this case, for the extent that a single graduate student working on the project, the maintenance cycle or latency is going to be wider than a project that has more maintainers. But the project is open source. And so as a researcher, I learn the most from people who use the system into problems, maybe bring to my attention some assumption that I was wrong or some use case that I didn't consider. So kind of bringing that back to us is extremely helpful. I can provide support to that particular person. Like, we will do that as soon as we're able to get to that. And then if people want to collaborate and start contributing to the open source project, then that would definitely make some of this feature adoption and turning the project into something more product scale possible.
And in your experience of building and experimenting with FLOR and helping people adopt it for their own research and experimentation purposes, what are some of the most interesting or innovative or unexpected ways that you've seen it used?
This semester, I worked with an undergraduate student, Alexis Wan, who was being advised by Koshik, a programming languages professor at Berkeley. The way that she was using FLOR, she was generating traces to serve almost as training data for another model that then later would do code summarization or code recommendation, kind of like you might hear Autopilot or Copilot from Microsoft. And so here, we have FLOR as a system that provides virtualization of our model training executions. And what she did was she enlisted in a Kaggle competition and she tried to beat the leaderboard scores. And in that process, she would generate a repository with 300 versions of explorations. And she would backtrack and check out a new branch and then continue that exploration. And so what she's generating now is this extremely rich record of executions of all of the things that she tried, which now, because she has FLOR, she's able to go back into them and insert logging statements after. But instead of inserting logging statements, she can add program analysis instrumentation for like dynamic analysis. Systems like BAMSA, for example, might do similar behavior. And so she's able to produce these really rich traces to accompany the code, which can then be fed to a model so that it has more signal for making recommendations. And so one of the applications that she was looking into is, can you detect when the documentation of a function diverges from the implementation using those means? So I guess using FLOR as a means of generating data for a deep learning model was something surprising.
In your experience of building the FLOR project and maintaining it and helping to use it for research and doing research on it in your own studies, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
I think I answered that question before. And I think one of the surprises here was to see this record replay of a Python execution being something that was within the proper domain of database theory. So when I was explaining to them, to the database community, how I replay a Python program efficiently, just really fast replay of a Python program. I was able to explain that to them using a transaction model, which is just a sequence of writes, and base it on contributions from the 80s with Aries. So we already back then see parallel transaction recovery, which is something that was kind of similar. And so I kind of felt like that connection was not something that was immediately obvious to me. It also seemed to kind of explain why the overhead constraints were so strict in our use case, but they seem to be so different in other papers that did record replay. And that was more because we were kind of taking a simpler execution and turning it into something more complex than people in software engineering or systems might be doing.
And for people who are dealing with some of these challenges of being able to quickly manage sort of rapid experimentation cycles of their machine learning models, what are the cases where FLOR is the wrong choice?
Our parallelism gains have rely on the number of epochs that you have. So model training jobs where you only have a single epoch, like scikit-learn models, or some that have very few epochs. Sometimes we've heard of cases in robotics and reinforcement learning where the model might be trained for 1 or 5 epochs, but each epoch takes a very long time to train. Then it's not such a good case because there's just not that much speed up you can get from parallelizing.
And as you continue to iterate on the FLOR project and as you're nearing the end of your studies, what are some of the things you have planned for the near to medium term? And what do you view as sort of the long range future of the project once you do complete your studies and move on to whatever's next?
Yeah, so the paper that I'm working on right now, the extension of FLOR that I'm focusing on, is an extension on time so that we're able to quantify and answer questions involving change over time. So what that might look like is in the refactoring case, someone had a model training pipeline that they wrote in TensorFlow, and then again, another one that they would like to write in PyTorch or Hugging Face. When it's time for them to ensure that the refactor succeeds, it's a question about how two executions compare. Another diagnostics pattern is that people will they don't just try something and then do analysis to see what went wrong. They try something, then they try something else, then they try something else. And then once they've exhausted all their hypotheses, they don't know what's going wrong, then they kind of drill down. So by the time that they drill down, they've collected this collection of executions, maybe 10 or 15. And so they would like to ask questions over the set. There are questions along like, when did this go wrong? Had the segmentation masks been fractured all along, or is it something that I introduced when I added this particular change? What would have happened if I had eliminated this hyperparameter modification? So posing those kinds of questions and answering them is ongoing work. And we want that to be able to scale with the questions, not with the number of executions, of which there will be many. So we want the interface to be such that the user can post a query, maybe in something like SQL or Pandas, and insert a logging statement in the latest version of their code, and then use software patching techniques to take that logging statement and push it into every version in history. We've been doing the automatic version control. We have the checkpointing. And so then the system picks an intelligent re-execution schedule to collect the data and answer questions. It could be in the aggregate, or it could be approximate query processing. So the next extension to FLOR is kind of lengthening the horizon so that we get some visibility across how things change, not just the latest execution of model training.
Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this week, I'm going to choose a movie I watched over the weekend. I saw The Batman, so the latest reboot in the long series of reboots for the Batman franchise. And it runs almost 3 hours, but it was actually a very well done movie. Some good acting, a good take on the character. So definitely recommend that for folks who are looking for something to keep them occupied over a long evening. So with that, I'll pass it to you, Rolando. Do you have any picks this week?
Well, one pick I'll highlight is on a TV show, since you were speaking about a movie. My wife and I have really enjoyed the show Severance on Apple TV. I think just one season has been out right now, but it was definitely a binge-worthy show. So definitely would recommend. And as far as the tech goes, I've become a really huge fan of code spaces with GitHub. So that has made it really easy for me to take my prototype and hand it to undergraduates and see the work that they're doing and kind of be able to inspect their work and also manage their environments, because that's something that people who have TA computer science classes, like, you spend most of office hours setting that up. So check out code spaces. It might help you manage your IDEs. And if you're working with other people and managing their IDEs, that'll also make your life easier.
Awesome. Well, thank you very much for taking the time today to join me and share the work that you've been doing on FLOR. It's definitely a very interesting project and an interesting problem domain. So I appreciate all of the time and energy that you've put into helping make it a bit more of a tractable problem. So I appreciate that. And I hope you enjoy the rest of your day.
Thank you so much.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcasts.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.